So the last thing we want to look at as far as Lewis structures go this year is something called a coordinate covalent bond. And if you notice, these are bonds in which both electrons come from the same atom rather than one electron from each atom. So you see this a lot in polyatomic ions. Any atom with non-bonding pairs of electrons, like nitrogen, phosphorus, sulfur, the halogens, can be a donor for a coordinate covalent bond. Oxygen oftentimes is the beneficiary of a coordinate covalent bond, and you're going to see what happens there. So again, more often than not, coordinate covalent bonds are going to come into play, not always, but usually with polyatomic ions. So let's just take a look at a couple of examples. So I'm going to jump back to the one cation that you needed to learn, and that is ammonium. Okay, so nitrogen has that 5 electron arrangement. So it makes sense that to make ammonia, NH3, you take the 3 hydrogens and bond them to each of nitrogen's bonds. But now you've got a situation where you have a 4th H to have to come down. So what actually happens is that 4th H is going to lose its electron. So even though you have this situation where if you formed a bond here, it would be 3 bonds, this electron is actually pretty easy to lose from hydrogen. So hydrogen's going to lose that electron. That's going to go off somewhere else. And you're going to form this coordinate covalent bond here with the hydrogen's valence shell that's empty and nitrogen's valence shell or orbital, in this case, that's full. So you wind up with a Lewis structure that looks like this, but again, remember you have to put it in brackets and show that it's positively charged. So that's what the ammonium ion looks like. And it results from hydrogen losing its one lone electron and then mooching off of nitrogen, coming and sitting down on that non-bonding pair, normally non-bonding pair of electrons around nitrogen. So again, not too many cations, but there's an example of what happens. Nitrogen will donate or allow hydrogen to use its pair of electrons. Other bonds you see happening, like we did ClO minus, if we do ClO2 minus, what's going to happen? So you can get a coordinate covalent bond. Chlorine is actually going to be, it's going to be weird. Chlorine is going to be the central atom. So you've got chlorine forming the normal bond with oxygen. Okay, so there's ClO minus. Where in the world is that other oxygen going to go? Well, these oxygens this oxygen, as the extra one, is actually going to form a coordinate covalent bond with one of chlorine's pairs. So normally oxygen will look like that. But what it can do is it can take this electron and shift it. So it's going to take that electron and actually make a new pair over here so it's empty, and then it can sit right there and share a pair of electrons. So that's another example of a coordinate covalent bond. So this year we're going to use the coordinate covalent bonds a lot to help us support what's really happening in the structure. So again, to draw it, you would make it look something like that, and then give it the minus. Okay, so same is going to hold true for these guys. You're going to have chlorine as your central atom. The 3rd oxygen is going to coordinate covalent bond. The 4th oxygen is going to coordinate covalent bond. Okay, so all of these are going to be very similar. You're going to see the same kind of thing happening, for example, if I do phosphate. We did phosphite in the last one. If I do phosphate in this one, okay, think about phosphite looked like that. Where is the 4th oxygen going to go? Because the only difference between phosphite is this 4th oxygen. Well, you can guess. Oxygen is going to coordinate covalent bond. It's going to move its electrons around, and it's going to share that pair of electrons. So in the long run, it's not going to look any different. That coordinate covalent bond is not going to look any different from what you had with the other three bonds. 3 pairs of electrons around each oxygen and a bond to phosphorus. So notice that in all of these cases, the octet rule has been satisfied. Okay, so that's the important thing, that we're satisfying the octet rule. So why don't you give, let's see, should we do NO3 minus? Go ahead, give that one a shot, see what you come up with. So keep in mind the pattern that I've done. Oxygens in polyatomic ions, oxygens kind of form the shell around the outside. So go ahead and give NO3 a try, NO3 minus a try. All right, so nitrogen's going to be my central atom. I've got, it's only -1. So if you remember what we did for NO2, I had 1 oxygen and the extra electron. And then I had the double bond to the other oxygen. Okay, so that guy went down here and we formed a double bond. Okay, so with this third oxygen, what's going to happen? Got a coordinate covalent bond going on. That NO coordinate, that NO bond is completely from nitrogen's non-bonding pair of electrons. So you've got this. So that's one. Here's the other. And then you have a double bond for that oxygen. So 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Everything is fulfilled in terms of the octet. It's just that we got to it a little bit weird. We had to add an extra electron, and we had to form a coordinate covalent bond. If you try these problems with polyatomic ions and you have trouble, don't sweat it too much. A lot of what we do is going to be with neutral atoms. So it's not that huge of a deal if you are not getting these polyatomic ions. It's not like your grade is going to suffer immensely. Well, you'll, get 1 or 2 wrong here or there. But I know this is kind of hard to take in. So practice it, see what you can. Watch the videos a couple times so you get a feel for it. But this is as complicated as we're going this year, this idea of coordinate covalent bonds. All right, so now you've got a couple other problem sets to do. 10 through 13, I think, is the whole shebang with all 3 videos. Good luck with those.